On to chapter 16. So we're going to talk about aromatic substitution in this chapter. The bulk of it's going to be electrophilic aromatic substitution, where we're adding positively charged things to benzene rings. We're going to talk a little bit about nucleophilic, which looks a lot like an SN2 type reaction, but has a different mechanism. And we're going to talk a little bit about designing a synthesis, although it's probably not going to be as difficult as the ones from previous chapters, stuff like that. So one of the very first reactions you guys learned, right, is adding something like HCl to a double bond. Okay, right? So double bond, right? So with HCl. Right, so if you remember the mechanism, right, so this has negative character to it, positive character, negative character to these things, right, because chlorine's a lot more electronegative than hydrogen, right, so it's going to be negative character. Here you've got 4 electrons in between two carbon atoms. You have a lot of electrons, right, so that goes there, pushes that guy over, right, so you get this intermediate, right, positive charge on one side, right, the H goes on one side, plus Cl, right, and then the Cl comes back and attacks, right, so you end up with, this product, right, an H on one side and a Cl on the other. Okay, that's as basic as you can get. Turns out when you add bromine to it, right, and if you had, right, so the analogous reaction, right, if you had chlorine on there, it would work the same way. You would just put chlorines on both sides, right, or bromines. But for bromine, it turns out what happens is you actually end up getting just one of the bromines on there, okay, on one side of this double bond, and the double bond remains, right? So we need to be able to keep that the aromaticity, right? So maintain the benzene ring on this in this structure, right? So like that. So we need to do this, and so in doing so, we're going to add just a single one of these to the reaction, right? And in fact, what we're going to need to be able to do this is a Lewis acid. Okay, so like that. So something in this case would be iron tribromide, iron 3 bromide, something like that. So, but we're going to be saying this a lot, the same mechanism over and over again, all throughout this chapter. Okay, so the way this works is it turns out that, right, so the iron is this, since this is a Lewis acid, okay, right, it's searching for lone pairs, right, and there's a whole bunch of them around these bromines, okay, and so what ends up happening is it takes one of these sets of lone pairs and moves it there, but in doing so it actually pulls the 2 electrons onto this bromine to make this intermediate here, Br. And since it only has 3 sets of lone pairs, right, you end up getting a plus charge, plus FeBr4 minus. Okay, so you end up making this charge. Now you've got something positively charged, right? Right. So you have the lone pair, or the double bond here, right? So this is going to attack that to make this intermediate here. Right, and the nice thing is, right, you end up getting a positive charge here, right? But the nice thing is, right, you can get these resonance structures, right? That's why we were learning about these resonance structures, right? So the double bond is there. Now it skips over and goes here, right? Right. You can then move this guy. Which puts the positive charge there. Right? How about that? But right, so these, right, so all of these things exist, right? But what's going to happen is, what it really wants to do is it really wants to reform this the benzene ring here. So what it does is it it's going to rip off the hydrogen where that bromine is attached, right? To basically reform the benzene ring and go there. Where your positively charged thing attacks, that's the hydrogen that gets ripped away. These two electrons in this bond here are going to go to reform the benzene ring. That's how every single one of these things works. You form this positively charged species, the benzene attacks, you get the resonance structures that come in here, and where the positively charged thing is added, the negatively charged thing that's also there is going to come in and rip off the hydrogen to reform the benzene ring. That's how all of these are going to work. You're going to get sick of these by the end of the chapter. Okay? But the big thing to notice, right, so if you have regular bromine, right, so with that you add bromines on either side. When you have bromine in the presence of a benzene, also you need to add the Lewis acid. You don't do this, right, because you're destroying, right, so you're not going to just add it across there, right, because when you do that, you destroy the benzene ring structure of this. You're going to just add one bromine, keep the benzene. That keeps the stability of the benzene, overall stability of the molecule. Now, chlorine works the same way as bromine, but instead we use iron chloride in here, just so we're not mixing up the halides here. So with that, so we're not, but again, it works the exact same way. You have to, fluoride works a little bit differently, right, because F2 isn't going to react quite the same way. But again, we make an F plus, and it's actually this F theta. BF4 structure here, but ultimately what all this extra stuff is just to make F plus. How about that? So iodine, again, it's one of those that doesn't work quite the same way, but you need iron in the presence of with presence of copper 2. That's the one we're mostly going to be talking about. So iron and copper 2 chloride, right? We're going to add this on here, but again, you're going to make it generates an in situ I plus. How about that? And so again, it gets reacted with the benzene. Nitration. In this case, we're taking nitric acid in the presence of sulfuric acid. So this would be something like so nitrogen and nitric acid, sulfuric acid. This is typically called aqua regia because that's in concentrated forms. It's what forms. It will actually dissolve gold. One of the few things that will actually dissolve gold. But in this case, what you're doing is you're adding the extra acid and the sulfuric acid will release a water molecule here to generate NO2 plus, right? Which then can again be react with the react by the benzene, come in here, form these, the negatively charged thing comes in, rips off a hydrogen, reforms the benzene. But again, it's this positively charged species that forms. Now, just as a quirk. Right, so we can't add an NH2 directly, okay, to a benzene ring. It's well, you can, but not in this, with this technique. So one of the things you actually need to do is, if you want to add an NH2, what you have to do is you have to go through an intermediate. You have to go through this nitro intermediate, right? So you can't go here directly. NH2. You can't do this directly. Okay, what you have to do is you have to go through here, HNO3, H2SO4, right, to add the nitro group on here, and then hydrogenate it down. Okay, you can't generate an H2 positive species. It's too difficult to do, so we have to go through this alternate route. Okay, so with that, because we can't get there directly. So with that, so do be careful, right? Now for sulfonation, right, it's the same thing, right? We're generating an SO3 plus, right? That gets attacked, and you make the sulfonic acid. So with that, so same mechanism. Okay, now hydroxylation. Now this would be really nice if we could do this. It's actually quite difficult to do. Your liver's really good at it. And so this is actually how a lot of pharmaceutical drugs are metabolized, right? So they throw on hydroxyl groups to make them more water soluble, so they can be go into the going back into the bloodstream to get excreted through urine and feces, stuff like that. So if you want to do this, you're going to have to do some sort of enzymatic process, stuff like that. So there are other ways of doing it, but stuff like that, but not from this chapter. The again, this can be incredibly difficult to do. So we're not going to worry about it. So the things to remember, right? So if you want to put a fluorine, right? So if you want to put the halides, fluorine, you're going to need this F-theta. Benzene bromine and chlorine, right? Both of these work just with the normal iron, stuff like that. So the normal halide gas and the iron salt, stuff like that. So and iodine needs this copper chloride, stuff like that. So if you want to add a nitro group, right? Nitric acid, sulfuric acid. If you want to add a sulfate, right? So this SO3 and sulfuric acid, so with that. But if you want to put an NH2 on there, right? You actually have to go through this nitro intermediate and reduce it down to the NH2, so with that. So okay, so alkylation, right? So with that, right? So this course is really making when to make on making new carbon-carbon bonds, right? So what do we need, right? So if we wanted to do this, right, we can predict what we were going to need. If we're going to do this mechanism, if we want to make a carbon, if we want to add carbons to it, what do we need? Well, we need right? So if we need to add a carbon plus, right? So add there, right? You go through this, right? Oop. Right? You come in here, you get the resonance structure, right? You have some sort of base in there, rips this off, and reform the ring, right? It's the exact same mechanism, right? We've been dealing with. It's just now, right? We need to generate some sort of carbon plus, carbocation, right? But so. How do we do that? Well, same way, very similarly to what we were doing on the previous ones, right? So we're going to take our carbon, right? Carbon, chloride, right? And add a Lewis acid, right? These guys here are going to come attack there, and in doing so, pull those electrons away to form this. Positively charged and AlCl4 minus. Now this can get attacked, right? Now this can get attacked by benzene, and away we go. So with that, so okay, it's the exact same thing that we were doing before. It's no different. Okay, so again, the mechanism. This comes in. You generate a positively charged thing. The benzene attacks it, and then where you added that thing, that hydrogen gets ripped away to reform the benzene over and over and over again. Those are the 3 steps. Okay. Now, the nice thing is, okay, if you cannot do this, that needs to be. There's a reason why it's called alkylation, right? Because you're on an alkyl group, a straight, a carbon-carbon, like a regular carbon-carbon. Single bonds, right? So it's a regular straight chain. If you have a halide on a benzene or you have a halide on a double bond, this won't work. Okay, which is nice because if you have, you can get some selectivity on this, right? So if you had this structure here, right? Cl. Okay, well actually, let's. There's some complications with it right next to each other. Okay, so if you had this blue one and you had this green one or red one, right? So you'd be able to only react here. Okay, you could get selectivity over this chlorine over that chlorine, right? Because this chlorine is on a double bond. Okay, same thing goes with this one, right? Right. So here we go. Keep the colors the same. Cl versus Cl, right? You would get reactivity there and not on that red one. Okay, so it's nice to be able to take advantage of that sometimes. Okay, so there is some quirks about this. Okay, so we're going to be talking a little bit more about what are called electron withdrawing groups. And basically what happens is, right, so let's say I have this, let's say I have a nitro group. Okay. If you draw this out with all of the lone pairs, notice how this is a positive charge and that's a negative charge. Okay. What ends up happening is, because this positive charge is here, what's happening is it's sucking electron density there. It's sucking it away from the ring, and so if it's sucking it this way, it's going to be attracted to this. It's not going to have enough oomph to be able to go in and attack. Okay, it would be sort of like having a bullet that only had half the gunpowder in it, right? Stuff like that. So the you wouldn't be able, it wouldn't fire nearly as hard as one that was full. Okay, so like that. So whenever you have something that has basically has a double bond right next to the ring, so, or double or triple bond, right? So C double bond O, okay, N double bond O, right? S double bond O, C triple bond N. Whenever you have one of these guys right next to the ring, okay, right next to that ring, this won't go. These are deactivating. Okay, so with that, so these are electron withdrawing groups. Okay. Now, on a side note, what will happen is if you have a some sort of amine where you have these, okay, primary, secondary, tertiary amine, okay, where you have these lone pairs right there, what ends up happening is this doesn't work either. Why? Well, it turns out that this thing kind of mucks up your it binds to your aluminum, your Lewis acid, your aluminum chloride, and prevents it from going. It binds up your catalyst. If you don't have a catalyst, the reaction's basically not going to go. So like that. So you can't have this electron withdrawing groups on there. So you're gonna have, if you want to do this, you have to design around those. Okay. I'm not going to be as strict on this. We'll talk about that later. Or have the nitrogen on there. So like that. So you do have to be careful about how you try to get there. Okay. So that the other issue, and this is actually probably the biggest issue, well, this one here, is, well, actually the next issue is sometimes you actually, it's tough to stop at one. These carbon, when you do an alkylation, it actually slightly activates the ring even more, right? So you can go in and make a second product, right? So if you put a lot of this alkyl chloride on there, like that, so you can get a lot of these extra groups put on. If you want it, you know, the minor product may be the single one on there, but you may get multiple ones put on. That happens, stuff like that. So, but probably the biggest issue is that you can sometimes get rearrangement, right? Because if you remember back, right? So if you have this CH3H. Right, so what's the first step of the mechanism, right? So aluminum, you have aluminum chloride, right? So the lone pairs are going to come, right? These guys are going to attack there, but in doing so, it pulls that away, right? So you end up with the carbocation, right? Now this is right. So that, right? That's a primary carbocation. That is a terrible idea. Okay, so what can happen is this hydrogen can shift over there, and in doing so, it stabilizes that carbocation. Now it's secondary. That one the molecule can live with. Okay, and so sometimes what ends up happening is instead of getting it, particularly if you're trying to add on a primary, you end up getting the wrong carbon attachment. The carbon attachment is wrong. Okay, so with that, so instead of attaching through carbon 1, where you want it, because that's where the chlorine is, you end up connecting through carbon 2, because that's how it stabilizes the molecule. Stuff like that. So your major product may be this one here, and you get a little bit of that, but you're going to have some issues. So do be careful. Okay. Okay, so here we go. So how do we explain what happened? Right, so and I'm going to draw it like Cl, CH3. Right, so you'd expect the attachment to be right there, right? But what ends up happening is like that. You expect a CH2 here, and then you go into the T-butyl group, but that's not what we see. So what ends up happening, right? So you end up having, right, your AlCl3, right? Right, so this lone pair comes in, attacks the Lewis acid, right? But in doing so, it rips off those electrons here to make this intermediate. Positive charge there. Right. Again, you're talking about a primary carbocation. So with that, so this guy here will shift over. There. Now, this is what gets attacked. Oops. Right. Plus AlCl4, right? Minus that grabs that hydrogen, reforms the benzene, which gives you that. Okay, so what's happening is you get a methyl shift over here to now to form this, right? And now that's tertiary. That's fantastic. Okay, so with that, so now the benzene is seeing this intermediate here, right, to attack. Right, so it adds this guy through that positive charge there. Stuff like that. So to give that there, sorry, I forgot to put the positive charge there. The AlCl4 comes in, rips off that hydrogen to reform the benzene, and there you go. So that's how you explain it. Okay, so one of the ways that you can get around this, okay, is to do what's called acylation. Okay, so instead of going through a carbocation, well, you still go through a carbocation, but what you do is you have a C double bond. You connect through a C double bond to O. Okay, now this actually works pretty well. It's a very similar mechanism. Okay, where you have the aluminum chloride. So you have the same mechanism we've been seeing. Okay. Lone pair comes in and attacks, pulls this way to form this. Plus AlCl4, right? So, which we've been seeing, for a long time. But what happens is we get this resonance structure here. So it takes this set of lone pairs, comes down here to make the fourth bond to the carbon. The nice thing about this is that it traps the carbocation just at that carbon, so you never get any more rearrangement. Okay, so the other thing that it does is that, notice how, right? So when this comes in and attacks, you add the benzene comes in and attacks, right? So that's going to attack there, right? So you end up with this product here. This is, right, so remember when we said having a C double bond O deactivates this ring? Well, that's exactly what happens. So when you add it once, right, you suck electron density out, right, because it's C double bond O right next to the ring. That prevents it from adding a second time. Okay, it also prevents it from rearranging. Okay, so with that, so because this guy here stays where it is. Okay. Okay, so here we go. Predict the product. assuming no rearrangement here. Right? It's gonna want to attach right there, right, wherever that chlorine is, right? So it's gonna attack right there to make it like that. That's it. Now, for this one, right, it just attaches again. It attaches where that chlorine is. Okay, here's where the chlorine is, right? So it's going to attach there, where that chlorine is, and essentially displacing it. Like that. That's all it is. This is the same as that. It's just the drawing program just moved it around. But this is essentially what it is. Where that chlorine is, or where that bromine is, that's where the benzene, that's where the new attachment is. Not too bad. Now, substituent effects. Okay, so how fast can we know? So we've already talked about one of these things, right? So when you have electron withdrawing groups, right? So when you have, you know, that C double bond O, N double bond O, S double bond O, N triple bond, C triple bond N, those slow it down. Electronegative atoms also slow it down, right? Because they're having that same effect where they're pulling electron density onto it, right? But if you have electron donating groups where you have lone pairs right next to the ring, okay, but those can actually put those lone pairs onto the ring, okay, and so what ends up happening is you get the reaction speeds up, okay. But what ends up happening with this is you get this orthopara and meta-directing, okay? So in general, electron withdrawing groups are meta-directing, okay? So if you have the C double bond O, right? So C double bond O, S double bond O, stuff like that. So was it N double bond O, right? C triple bond N, okay? These are all, right, so with that, so, right, so with that, and then if you have, let's say, chlorine, bromine, fluorine, iodine, okay, these are all electron withdrawing. Right, but if you have things like just carbon, just like whatever, regular carbon, right, so COH, right, CNA, or nitrogen's on there, okay. So, but that's, and even this one here, this one drives people nuts, right? If you have, so even here, right? Even though this isn't quite as beneficial as these guys here, but again, you have lone pairs right next to the ring. These are electron donating. Okay. Now, here's the quirky thing. These guys here will tell you if you want to add another group onto it, it'll tell you where it wants to go. Okay. It turns out these guys here means that these are orthopara directors. Okay. Well, these guys are meta directors. Okay. So notice the trend here, right? If you have lone pairs right next to that ring, you're going to be orthopara directing. If you don't, if you have a C double bond O, S double bond O, whatever, so you do meta. Okay, that's the trend. Okay, so there we go. So here we go. So what does all this mean, directing? So let's say we have this group here. We have toluene. Okay. Oh, hey, we want to put HNO3, H2SO4. Okay. Oh, we know that. That's a nitro, right? So what is this, right? that, so if we have just regular carbon, this is ortho-para directing, right? So ortho, right? Ortho or para. Okay, so that means that we're going to get some, right? Some group that's going to go there, and some that's going to go here. Too. Okay, we're either going to add to the ortho position. Now, you're going to say, well, why don't we put it over there? Well, we did. We just take that molecule, flip it over. That moves the, that puts it over there, right? So, but that's so, right? We're going to say this group. Oh, it doesn't have any lone pairs. It's just a regular carbon group. Oh, that's ortho-para. That means it either goes there or there. Okay. Now, what if we say, okay, here we go. NH2. Oh, hey, it's got lone pairs on it, right? Oh, so if we add HNO3, H2SO4, right? Again, this is ortho-para, right? So we're going to get this mixture of nitro group here, nitro group there. Okay? Doesn't matter what this chemistry is. Does not matter what this chemistry is. The next group that goes on is going to go ortho-para. Okay? So here we go. So we have, so let's do it again. Right? Oh, hey, we have a, right, we have that C double bond O directly next to this double bond, right? Okay, so that makes this a meta director, right? So these are the meta positions here, meta, meta. Okay, so that means that that nitro group is going to go on there. Okay, well, it also go in there, right? But that's just the molecule flipped. Okay, so again, doesn't matter what this chemistry is. This is the directing group. Okay, it does not matter about this. I cannot emphasize this much. It doesn't matter about the chemistry, right? All that matters is how this is directing. Okay, to whether it goes ortho-para or meta. There we go. Now, why does this happen? Okay, it all has to do with right, so these resonance effects. Okay, now let me show you what happens. Let me see if I can get it. Okay. So let's say we have a carbon group. That'd be the easiest thing. Okay. Okay, we're going to add our E plus. Okay, that comes in, and we would predict that this would be an ortho-para director, right? So let's put this in the ortho, and the electronics work out the same way, whether we're going to add ortho or para. Okay, but let's add it ortho. Okay. So that puts, right, we're going to put the E on this, right, because we know it's ortho, right? So that puts the positive charge there, right? Now we're going to do our resonance structure. We go there, right? Right, we have the skipping effect. We're going to skip there and go here, right? We can draw another resonance structure where we move that there, right? So again, we're going to have that skipping effect and going here. Oh, look what happens. We put the positive charge there. That is a tertiary carbocation. Okay, that is a good thing. That's why if you were to put this, if you were to put the E group, say here, you would still get this resonance structure where you put it there. Okay, Now, if you were to instead put it on the meta position, right? Put it there, right? We have the skipping effect, right? Because we started here, we skipped to there, we skipped to there, right? So where would we go, right? So we would, right? We'd go here, we'd skip to here, and then we'd skip to here, right? So here's where the carbocations would end up, and we'd never get to this chance. We'd never have this opportunity to have a tertiary carbocation. The molecule knows that if I add here, I'm not going to be able to get that right next to each other, right? So this doesn't form. That's why this goes. Same thing happens, okay, with other ortho pair directors, right, that have lone pairs on them, right? So let's do nitrogen. E plus, right? So we're going to add that there, right? So let's add to the same thing. We're going to add to the ortho position, which puts the positive charge there. Right? We're gonna move this over, which skips it, puts it there. Right? Right? So we're gonna move that down there, which then puts it right there. That's a good thing. Puts a positive charge there. Why? Well, what happens is that now, again, you can take these lone pairs and move them down here to make an additional resonance structure. Right? So you can move these guys down, the lone pair down here, to make this fourth bond with that carbocation. Remember, if you have this, if you put this into the meta position, you can't take advantage of that. Okay, so that it knows that you're going to be able to, by putting it into the ortho position or the pair position. If you do the pair position, again, it works. Electronics work the same way. You're going to be able to take advantage of that potential resonance structure here. Okay. Now, for meta directors, okay, so remember, nitro is probably the easiest one to see. Halogens, again, it's the same deal, right? You can get this. You have a set of lone pairs there that they can help. Now, they're not going to be happy about it, but they can do it. Okay. Now, for electron withdrawing groups, right? So the easiest one to see is if you have a nitro group, right? Because the way that you can draw this out, right, negative, positive, like that. Okay, so again, let's say this was, we were going to put this into the ortho position, right? So just like we were doing before, right? So the nitrogen has to have the octet, right? So this is how this is one of the ways that you can draw that out. Okay, so again, He puts the positive charge there, right? Move that there. There, so that puts a positive charge there. Let's move that there, and look what happens. You have two positive charges right next to each other. Okay, that is a bad thing. Okay, so like that. So it's not going to do that, because if I do a resonance structure, then you're going to have two positive charges right there. Now, if instead it came in and put it in the meta position, right? Okay. right? You're going to have it here, right? Remember, we have the skipping effect. It's going to skip that one and put it here, positive charge there, and skip it and put a positive charge there, right? If we go through these resonance structures, okay? At no point do we have two positive charges right next to each other, okay? So the molecule knows, hey, if I put it here in this meta position, we can keep two positive charges right next to each other. Now, it's not real happy having two positive charges on the molecule, but it can at least avoid this sort of positive-positive clashing. Okay, so that ends up being, right, so when all said and done, you end up with that molecule here at the meta position. So this is what drives it, right? So these are what drive where the next thing goes. Doesn't matter what it is that you're putting on there. This tells you where that's going to go. Okay, so with that, so this we just did, right? Well, let's go ahead and do it. What the heck? Let's do the whole kit and caboodle. CH3Cl, AlCl3, and then we're just going to do the para, like that. Okay, what's the first thing that happens, right? So we have our catalyst here, right? That's going to come there, that's going to get attacked there, right? Because what do we need to generate? We need to generate this CH3 plus and AlCl4 minus. Okay, again, that's going to attack there. Okay, so this is all generating the plus charge thing, right? So that's the technical term, the plus charge thing. Right, so, right, we know that the CH3 is going to go here, right? That puts the positive charge there, right? And then again, we're going to have these resonance structures. Okay. Now you could have this guy going here, right, to just circle around the ring. Or what you could do is you could have this guy, one of those sets of lone pairs coming down here to make this resonance structure there. Okay, so there's a lot of really nice resonance structures that we can draw. Well, but the big thing is, right, this guy is going to come in, grab the hydrogen where you've added, right, and those electrons are going to come there to reform the ring. Okay? So there we go. Oh, okay, same deal. With this one here, right? You come in here. You want to try to avoid having again. You add the Lewis acid rips off the chlorine, right? So with that, so to make the positive charge, the carbocation here, this comes in and adds, but we're going to add the meta position so that when you draw the resonance structures, you don't have two positive charges right next to each other. Okay. The aluminum chloride comes in and rips off the hydrogen where you've added to reform the ring. There you go. Okay, just in summary, right? If you have lone pairs right next to the ring, it's ortho para director, or just a regular carbon, regular alkyl group. Those are all ortho para. If you have a N double bond O, C double bond O, S double bond O, C triple bond N right next to the ring, it's a meta director. Okay. Now those are also deactivating. Halides are deactivating even though they are ortho para director. Okay. Okay, now what if you already have two groups on there, right? We talked about having one group on there. That's pretty easy. What happens if you have two groups on here, right? So it's pretty nice, right? If they can be right. So CH3 and O2, right? So right, this is orthopara, right, and this is meta. Okay, so where's the orthopara? Well, para's here, right? This is right. So ortho, right? Well, what's meta to this? Well, meta. Ooh, let's do some blue. Meta, right? So you're going to definitely get stuff added here and here, right? They reinforce each other. Okay. Now, if you have something, let's say instead you had CH3 and OH here, right? So they're both orthopara. Okay, now what happens? Well, you kind of have to go back to that list, right? So this would be ortho, right? Right, para would be here, but that's already taken. So ortho, para. Okay, you have to figure out which one's stronger, and it turns out that this guy is stronger. So what you're going to end up with is this guy winning, and your E group is going to go there. Okay, you kind of have to look at that chart. I'm not going to necessarily throw that at you, stuff like that. So saying which one's stronger or not, just because I don't like, stuff like that. But for the most part, you can make the trend is right. So remember when you were naming the benzenes, right? If you had two base structures, right, it's always the other base structure is always going to be higher priority than toluene, which was the methyl group. Same thing here. Everything's going to be a higher priority than the than just really an alkyl group. Okay, if you have an amine versus an OH, right? So where did that comes into play? That's a little bit more difficult to predict. But everything's going to be higher priority than just a regular methyl group or alkyl group. Okay. Now tri-substituted. Okay. Now you do have to be so you do have to be. Sorry, we're talking about tri-substituted. The other thing you do have to worry about is if you have things that want to direct here, right? So both of these are orthopara directors, right? Right, because that's a alkyl group, right? And this one has lone pairs right next to it, right? So they're going to go here, here, and here. They're both additive. Okay, to those three positions. The problem is this one is not going to get added to, right? Because it's just sterics. There's just too much stuff. It's too hindered to get in here, right? So you're gonna get this product. You're gonna get it where you're adding here, and you're gonna add it here. But you're not going to get it one where it's right there. It's just too hard to get in. It's too hard to muscle your way in. So you're going to just get these two. This one isn't going to be formed where you're adding it right there. Okay? This is a nice multiple choice question. Okay, so predict the products. Okay? Here we go. Always like predict the product questions. Okay? Right, so we have that. Okay, doesn't matter about this, right? We're just doing this, right? So this is what? This is orthopara, right? So we'd want to go here and here, right? What is this? This is meta, right? Oh, hey, meta. This is meta, right? Oh, okay, so we're good. We're good in this case, right? CH3. Right, we're definitely going to be adding it there, right? We'd also add it there, but it's just same molecule flipped. Okay. Don't forget to draw in your lone pairs, right? Right. Okay, so this is an orthopara director, right? Because it has lone pairs, right? So it's going to go here, here, and here. Okay. This is an orthopara director, right? Because again, it's got lone pairs, so it's going to want to go here, here, and here. Okay. So, but what's the problem, right? We can't, because we have this 1, 3 here. This isn't going to be an option. Okay. So you notice I didn't even write what the reaction was. I was just going in and doing the ortho director, and then now we can come in and, oh hey, it's this chlorine reaction again. It doesn't even matter, right? We got to figure out where it's going to go, and then we can figure out what's going on. Okay, so we're going to get a chlorine here, and we're also going to get a chlorine there. And that's it. We're just going to get these two products. We can't add there. Okay. So what about this guy? Okay. Well, what do we have, right? So this is an orthopara director, right? But this is a meta director. Okay, so orthopara, right, that's going to want to go here, here, and here, right? But this is a meta director, right? So it's going to want to go, well, it can't go there, right? But it's going to want to go there. So now the question is, which one's more powerful, right? Everything has priority over a methyl group here. So this wins. Okay, so the product that's formed is, oh, what is the reaction? Oh, it's Cl2. So we'll add the chlorine there, right? Like that. So there we go. Now, nucleophilic aromatic substitution, right? So electrophilic is probably the more important of the two, but this one can be quite important for what you're doing. It looks a lot like SN1, SN2 chemistry, but you remember we can't have an SN1 or SN2, or definitely, right? Because you're not going to have that fall away, right? So because that wouldn't be stable. You can't say SN1. You can't have SN2 on a benzene, right? Because you can't get like inside the ring to be able to do a backside attack. So that doesn't happen. Okay, but it does happen, right? But something happens, right? What turns out the mechanism is a little bit different. It turns out what's happening is, okay, oop. Okay, so what's happening is this guy is still attacking at that carbon, right? But again, we have 4 bonds here. What's going on is this is getting pushed down, sort of springing, pushing down, okay, to form this. Now, I'm going to show you why having that nitro group is great, right? So we put a lone pair there, which has a negative charge, right? ClOH. Remember that when we were drawing out the nitro? Remember if we drew this out? Ooh, that's good, right? Having a negative charge right next to a positive charge, right? That makes this really, really good, okay? So that stabilizes this thing, okay? And so what can happen is, right, but, you know, you could do a resonance structure where that stabilizes and moves things around, but what's happening is, right, this will actually kick back down, right, because we want to reform that benzene, and then we kick the chlorine away. Now you can say, well, why won't you click the OH? Well, okay, it does a lot, right? But what does it form? Well, it forms that. So we'd never be able to detect it. It just goes back to starting material, right? But instead, what we get is the OH going on in there, NO2, okay? So like that. So you're sort of like pushing the electrons down, right? So the electrons are in there. You're pushing it down here, and then they're collapsing back down and kicking off the other group where you added. Okay, and having this electron withdrawing group in this orthopara position works really well. It's sort of the opposite of what happens with this one, right? Because now we're dealing with negative charges, so you want to be able to put it right next to a positive charge, right? So, so having electron withdrawing group right next to, in this ortho pair position is really good because of these mechanisms, right? Because we can put a negative right next to a positive. So that works well. Okay, so here we go. This one it's a little bit more complicated, but what I'm going to do is I'm going to simplify this a little bit. This is really cool. This is the kind of stuff I worked on when I was at Pfizer. Stuff like that. So here we go. So we have an OH group adding to this fluorine here. Right, I'm going to put the NO2 so we can distinguish between the two. Okay, and again, we're going to add. We add this in KOH. Okay, so with that, and so what the OH, what that does, right? That rips off that hydrogen to give you from the phenol that. Now you get yourself a nice nucleophile. That's going to come in and attack there, and then push these onto that. Okay, to form this intermediate. Like that. That just collapses back down, right? And if we kick off the kick off the phenol, right, it would just go back to that. Right, but instead we're going to kick off the fluorine, and so we end up with those two rings now joined. Okay, so don't worry about, so that's essentially what's going on here. Okay, right, and having that nitro group there works really well, right? Because you can draw a resonance structure, right? So there, skip to put it there. We could put the negative charge there, which is really nice because it puts it right next to that positive charge. If we did a resonance structure for that, okay. So with that, so this is a nice way of putting those in. Okay, benzyne. So this is one of those things where it's a little bit quirky. We're not really going to talk about it much, stuff like that. So. But what can happen is what people have seen, what people have observed, is that when you do something like it under pretty nasty conditions, really forcing conditions, what ends up happening is you get substitution. Okay. And what happens is, this is pretty rare, but it can happen, you end up with this, as the name implies, with the Y and like that. Oh, I'm sorry. There, and then, I'm sorry. Right? So now you got this fourth bond, or you got to kick that away. So you end up with, let me redraw this. You end up with that. Okay, now that comes in. Now this acts like a really weird double bond. That adds there. Right? H on one side. Positive charge on the other. Plus OH minus, right? Which that comes in and attacks to make that. It's this really, really weird thing. Okay, and they've noticed this. Because if you label that, if you were to label this carbon, right, you would actually get half of them on this side and half of them on that side. You make this really weird triple bond. It's not necessarily something I'm going to test you on, but just be aware of. It's really crazy. And notice the forcing, I don't know if you can see this, but it's 370 degrees Celsius at 170 atmospheres of pressure. So this is incredibly forcing. It's not necessarily something that's done often. Something like that, but to be aware that yes, it does happen. Okay. So, but that's now for we're going to talk about a couple other things you can do with these aromatic rings. So one of the things it turns out is that if you have, let's say, CH2, CH2, CH3, if you add KOA or KMNO4, okay, turns out what will happen is you get oxidation, right? This one of its sole purposes in life, KMNO4, is to oxidize, but it cleaves off that chain, and what you end up with is just that first carbon as a carboxylic acid. Okay, and then the other stuff. Okay, so if you had, let's say, CH3 like this and added KMNO4, right, you would end up with OH. Like that. Okay, wherever there's just a regular carbon chain coming off of there, you're going to get a KMNO4, with the exception of a quaternary. Okay, you actually have to have that hydrogen there. Okay, so if you had this, CH2, CH3, right? This is resistant. That's a quaternary there, right? Because there's 1, 2, 3, 4 carbons on it, right? So if you hit this with KMNO4, right, this would be a resistant, but this wouldn't. You would slice there. You would have this, CH3, like that. Okay, so like that. So you would still react here, but that would be resistant. Okay, this is incredibly important reaction. Okay, they don't use KMNO4 anymore. What they do is actually use high pressure oxygen. So with that, you release your water. But this is terephthalic acid. This is your PETE. So polyethylene. So it's a CH2, terephthalic ester. So with that, so the number 1 Pete. Esters, that's what there's done. So you take the paraxylene, stuff like that. So they react with oxygen to make the terephthalic acid, and then you can react that with the ethylene glycol to make this. And this was incredibly important, because what you can do is you have like the plastic bottles that are kind of curved and shaped or whatever it is. That's what they were doing. This was, maybe 15, 20 years ago. This was starting to get really big. So the original plastic Coke bottles that had that, and I think Evian was the first one where it had the mountains around that. They used these PETE bottles because you can shape it. Something like that. So you can also use this for waterproof fabrics as well. So it's pretty nice. Okay, so here we go. So if we had, right, so like that. So predicted products, right? So CH3, NO2, right? So we're going to hit that with KMNO4, right? Well, this has a CH on it, right? So we're going to cleave those guys off, right, to give NO2. Okay. Now for this one here, right? Okay, notice that this is quaternary here, while this is primary, right? So this is going to be resistant to it, okay? So you're going to get this product here. Right, you're only going to get reaction there as opposed to there. Okay. There you go. Now, very similarly to this, if you have, what you can do is you can put a bromine on here. So this is N-bromosuccinimate, with that. So this compound here, what it does is if you have a hydrogen right next to a benzene ring, it'll replace one of those with a bromine. Okay, but again, it's one of those where a quaternary carbon doesn't get brominated. Okay, and the mechanism is this weird radical reaction, stuff like that. Don't worry about the mechanism. If you want to, it's here, stuff like that. But it basically allows the single electron to flow around the ring to do resonance structures and get stabilized. It's good, and then the bromine comes back and reattaches and stuff like that. But what happens is, so we have these same compounds. We hit it with NBS and bromosuccinimide. Right, so here's a hydrogen there, right? Right, so we're going to put a bromine there. We don't cleave off the ring. We don't cleave off the chain, but we leave it there. But there's a bromine that gets substituted right in. Okay, so over here. Again, there's no hydrogen here, so this is going to be resistant to it, but we can put one there. NBS. BR. Right? Now, if we had multiple ones, right? So we talked about so let's say we had CH3 and then CH2, CH3, okay, and we hit it with NBS, right? Well, this one has a CH2 or a carbon hydrogen next to the ring, and so does this one, right? So we're going to get one added to both. So CH2, Br, right? CH3, Br, right? So we're going to have it added to both, okay, assuming we have an excess of this. Okay. You're going to add it one here and one there. Okay. Now, the nice thing, okay, is that if you have, right, so remember we talked about this, if you know, these guys are going to be resistant to it. Right, just under regular hydrogenation conditions, palladium and carbon, or however you want to do it. Right, this one's the only one that's going to get reduced. Okay. There. Now, if you were to force it, right? So if you were to force it, you hit it with, say, H2 with 100 atmospheres. Palladium and carbon. This is from last semester, right? You would take down all. You would reduce all. That's just regular carbon. You would reduce all the double bonds. Okay, so it would end up being like this. Okay. So these are all just single bonds. Okay. Well, it turns out that if this guy, if the C double bond O is right next to that ring, now it has to be right next to it. Here, it won't do anything. If it's right next to that ring, H2, just regular conditions, it will get reduced, and specifically to a CH2. Okay. Now, the nice thing about that is, let's say we want to put this chain on there, right? If we were to add it, if we were to say, oh, we're going to do alkylation, right? So we would do, well, we want to put the chlorine on there, right? CH2, CH2, CH3. What would end up happening, the product that you would end up mostly seeing would be this. Why? Well, what happens, right? So we had AlCl3, right? Right, so this is going to attack there. What's going on here? That's primary carbocation. That's bad. So what it does is it shifts over here to form this. That's secondary. That's much better. So you're going to see this. So if you want to make this the compound with a straight chain, right? So instead of doing that, what you have to do is you have to come in and do a slightly different route to avoid this. Okay? So what you have to do is you have to come in and instead do the acylation reaction. Right? So this forms now this one doesn't move, okay? And so that comes in and attacks there, and eventually you end up with this. There, now you can go in and hydrogenate it. Because remember, that turns it into a CH2, CH3. Oops, CH2, CH2, CH3. Okay, so this is a nice route for adding these guys, for adding like directly at the end of a chain. Okay, you're not going to get this rearrangement issue, so you have to go through these two steps. You have to add on the acylation and then do the hydrogenation. And then that'll get you where you need to go without the possibility of rearrangement of the alkyl chain. The other thing is it stops here, right? Because after you add this first one, right, so with that it deactivates the ring and you're done. This one here, if you were to, even if you could do it, right, this is slightly activating, and so you would, right, because we can make the tertiary carbocation, and so, well, actually, so with that, and so you would actually probably get a second one on here with that. So there's that issue as well. Here, you stop at this first one and you're done. Okay? And so what we can do is that we can then go in, so with that. So now the other thing is, right, if you really force it, right, you can do both at the same time. Okay? So, you know, if you had this on here, if you had a nitro on here, you want to keep that nitro on here, you couldn't do that. Right, because you're going to make the NH2. It'd be good if you want to make the NH2, but you know, if you're going to take down this one, you're probably going to react that one down too. So you do have to be you have to be careful about how you want to do this. Okay, make sure your other groups are compatible with the hydrogenation. Okay. Now, big thing right now, we're going to get into the design of synthesis. Okay. Well, I'm sorry, we're not quite there yet. Okay. So with that, so remember when we wanted to make that compound, right? So with that, so right. So if we wanted to do this with the alkylation, what would we have to do? We'd have to use, if we want to go there directly, we would need this, right? We would need that right there, right? Which would form the CH2. If we did this, the alkylation, right, which would form that. This is primary, this is bad, right? This thing's going to get shifted over and to make the tertiary carbocation, right? So this isn't going to be able to work directly. So what we need to do is we need to come in here and we need to say, okay, emit defeat, and say, okay, we're going to do this way here. Where the C double bond O is eventually going to be this CH2 here. Okay, and so here we go. So we're going to add our aluminum chloride to make this. Like that. Now, we're going to do, to get here, we're going to have to do the hydrogenation. Like that. Right, that this C double bond O becomes that CH2 there. Okay, so like that. So it ends up going there like that. Okay. We can't do it directly through alkylation because we're going to have this moving around. But we can get to it through the acylation. Okay. Okay, so here, right, so the KMNO4, right, it'll take off if there's carbon-hydrogen bonds right next to the ring, it'll rip off the rest of the chain and leave a carboxylic acid group there. Again, with the NBS, if there's CH groups next to it, it takes off one of those CHs and puts on a bromine, right, for each chain. Okay, this is both for each chain. Okay. And quaternary carbons are unaffected. For here, hydrogenation, regular hydrogenation will just take down the alkene, right? If you needed to do it 100 atmospheres, it would take down the benzene as well. But if you have a C double bond O right next to the benzene, then you can do this, and it substitutes a CH2 for that where that C double bond O is, as long as it's right next to the ring, directly next to the benzene. Okay, now here's the synthesis part. Sorry, one step ahead. Okay, now this is where we're going to have to get into this strategy. We're going to have to say, okay, let's say we want to synthesize this compound, okay, from benzene, right? We're going to have to use what we learned in this chapter, right? We're going to have to know the actual reactions, but we're also going to have to do this where we know ortho-para directing, okay? And so here we go. Right, so what we need to do is we need to work backwards. Okay, so let's say what's going to happen, right? So like that. So we need these three groups to get put on there. Okay, so there's right. So we're going to put on 1, 2, 3, right? But we need to know which one's 1, which one's 2, which one's 3. Okay, so we're going to look at these individually, right? So like that. So what we're going to do, okay, is we're going to say, okay, right? So here are the three groups: SO3H, right? So with that, so CH2, CH2CH3, right, and then Cl. Okay, we're going to build this up. Okay. Okay, so let's say we're going to do this one here. Okay. Well, let's first, before we do anything else, right? So this right here, right, that is S double bond O, right? That's a meta director. Okay. This one here, this is an ortho-para director because it's just a regular carbon, right, regular carbon next to it. Right. This one here, right? This one here, right, has lone pairs next to it, so that's gonna be an ortho-para. So first thing you gotta do, you gotta recognize what those groups are. Okay. Now we're gonna do 3 different ways. Okay. We're gonna say, okay, let's say that's gone, and we had, right, and we had CH2, CH2, CH3. Okay. Cl. Okay. Well, where would this one go? Right, this one is ortho-para, right? This one's ortho-para. Okay. Well, ortho-para to this, right? Oh, there and there. Ooh, that's a good, and there. Okay. Ooh, what about this guy? Ooh, here, here, and here. Okay. That's a good sign. Okay. Well, but well, we got lucky on the first one, right? Well, what would happen if instead we started with this compound to do, right? We went Cl, right? Well, this one, right? This is a meta director, right? So it would want to go here and here, right? Well, what about this one? Well, this guy here, this is an ortho-para director, right? So like that, so well, that one wants to go here and here as well. Well, that's good. Okay. So like that, so well, what about this one? Well, that's a good sign. Okay. Well, what about this one? Well, what if instead we had this? Okay. Again, this is meta, okay, and this is ortho-para. Okay, so meta, right? Meta is going to go here and here, right? Ortho-para is going to go here, here, and there, right? Okay, so wow, they're all going to the right spot. Well, that's good. Okay, so which one do we want to do? Okay, so now the question becomes, okay, so they're all going to the right spots. We can put the things where, right? So if it's ortho-para, I'm going to say, well, we can separate out those. That's not a problem. Okay. So but this one here, notice how, right? So these guys here, that puts on, right? Because we want to have the SO3H go here, right? And eventually we want the chlorine to go there, right? We want the to go there, right? Let's not complicate that, right? And then we also want the CH2, CH3 group to go there, right? Well, that's no good. This is no good, right? Because these groups are going to reinforce to go here and here, right? So we can't do that, right? Because we have these two groups, right? Right, when we put on the chlorine, right, it's going to go there. Okay, so that's not going to work. If we go here, right, the chlorine and the SO3, right, they are going to be additive to right there and right there, right? So that's no good. Okay, when we add on the plus CH2, CH3, right? That's not good. So we have to go here, right? So these are the only places where we're added it up, where we're additive to be able to put the SO3 here. Okay. Now it could technically go here too, but we're going to say, okay, we can separate those two. It can't go there, right? Because it's too sterics are bad. Okay. So we're good, right? So we know what the last step is going to be. The last step is going to be we have to make this and then add the SO3H on there. Okay. That's going to be step number 3. Okay. Great. Okay, so now the question becomes, right? Now, how do we go from, right? We need to make this compound, right? Okay, so how do we make it? Okay, well, okay, if we added the CH2, CH3, right? We added the plus Cl, right? Where would it want to go? Okay, well, this is an orthopara director, right? So it's going to want to go here, here, and here, right? But we really want the chlorine to go there. Okay. Well, what if we said, okay, let's put on the chlorine, right? Well, again, this is orthopara, right? So that's going to want to go here, here, and here. And we really want the CH2, CH2, CH3, right? To go there. Well, crap. Neither one of these goes. What do we really need? We really need to go in, right? We need to have a meta director, right? Because these are meta to each other. So what types of things are meta director? Things that have N double bond O's, S double bond O's, say C double bond O's. Okay? So what we really need is this. Right? Now this, right, that's a meta director. Right? That's a meta director, right? Which we put it there and there. Well, that's perfect, right? Because we won't put that chlorine there. Okay, so now we can put on that chlorine if we have this compound here. Okay? So how are we going to do this? Okay, so what we really need is this, CH3, to be able to put on the chlorine, right? Right? So how do we make that thing? Ah, we just learned about that, right? We can take benzene, right, plus the acid chloride. We can make that. Okay? But wait a minute, that's not what we need for this reaction here, right? We need the regular alkyl, right? Because if there's a meta director, right, we're going to get this clasher, right? It's going to want to go there, right? So what we need to then be able to do, add this on there, is then come in and convert that into CH2, CH3, Cl. We need to add the alkyl first, right? Let's do this properly. Okay. Add the acylation first. Okay, that gives us a metadirector. Okay, we add that on there. We did the chlorine. We add the chlorine on there. That gets it into the correct position. Now we need to make these both into orthoparadirectors, right? So we hydrogenate that down to CH2, or down the C double bond O down to CH2. Then we can add the SO3H, H2SO4. There we go. It's a little tougher, right? But it's not so bad. You need to be able to realize what's going on, you know, so with that, your orthoparadirectors for the reaction. Okay. So here it is. We have benzene plus your alkyl chloride or acyl chloride. Do the Friedel-Crafts acylation. We then, that gets us to our metadirector, which puts the chlorine there. Okay. Now we need to make those both into orthoparadirectors, and we do that through hydrogenation to make this, and then we add on our sulfonic acid. There you go. Okay. So you're going to have a lot of these, right? We're going to need to know the order of addition is going to be incredibly important because of how the orthoparadirecting goes. Okay. So here I'll give you another example. Okay. So let's say we want to do oh, I know. Right? So let's say I want to do, paranitro-toluene. Okay. So if we were to put the nitro group on first, H2SO4. There. Okay. Now, this is a metadirector, right? Because it's an N double bond O. Where does that go? Here and here. Right? So if we continued on, CH3Cl, aluminum chloride, right, we would get this. That's not what I asked you to do. I made the para. Right? So what do you have to do instead? Notice how we have to put this on first, right? Because this is an orthoparadirector, right? Which will get you into there and there, right? So what we have to do is we have to switch those. So the order of operations makes a huge difference. We have to put the toluene on first, then, right, now we've got an orthoparadirector, right? Which would put it here, here, and here, right? So when we do the HNO3, H2SO4, right? They become there and there. So these are the kinds of things, right? So what happens if we start off with that, right? What would we get? Well, we get the product that we need. Well, what if we started off instead? We started off with the nitro group. Oh crap, we're not going to get into the right position because it's going to want to direct here. So you need to be careful about how you put things on. Okay, orthopara versus meta directing. Okay. Now the last thing is just a little bit of right. So combinatorial chemistry. Okay, so this was big in the 90s, but that for drug discovery. Okay, and so what they were doing is they were saying back in the 70s, up until about the 80s. The drug discovery was we make a bunch of different drugs and see what happens, and just observe and see if we get something that's better. And then we decided, you know what? let's go in and we'll just, we have these new screening capabilities, we have these new assays, right? We have a single target. Let's throw 100,000 compounds at this drug and see if any of them stick. Okay, so about that. So if any of these things work. Okay, and so what happens is you have all these different compounds with slightly different changes to them. So about that, and so and we're going to see what happens. And so the way that you make these, right, is you say, okay, I've got a pool that has, red, black, and green. Okay, red, black, and blue. Okay, now, so about that. So what we're going to do is we're going to split these, okay, into 3, and so here, there. Okay, so for the, and actually, okay, we're going to have red, red, right? Black, black. We're going to do all different combinations of these things, okay? So for red, red, okay, black, black, and blue. Okay. Now we're going to split these again. Okay. Now we're going to have red, 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 right? Right, and you end up getting, right, like all different combinations of these things, right? Black, so that you get all these sorts of different combinations, and it starts to sort of get exponentially larger, right? So you can kind of see that here. You have sort of AA and then BA and then CA. Basically what you end up doing is you split these things out, and then you do a reaction, and then you split these out again and add a reaction, and so you end up making all these combinations of these different compounds and stuff like that. So, and then what you do is you do high throughput chemistry, and so lots of times these things are about plates. They're 96 well plates. They're about yay big. They're standardized size. You can also have 384, which is basically 4 96 well plates on it. Stuff like that, and then you have robots that come in, and they'll come in and they'll and conveyor belts and stuff like that, and this is all automated. And you come in there, they'll pick up a plate and add your compound, you add your stuff to it, and then you come in, and then another robot puts it on the conveyor belt. It goes down here, it goes, picks it up, and does add something else to it, and then it goes in there and goes into an incubator and lets it sit for a little bit. And then another robot will come in and take it out and read get a readout on the plate and stuff like that. And so you can do like 100,000 compounds at the same time. So when I was at Pfizer, they had these high throughput screens. Every compound that was ever synthesized, every intermediate, if you need 5 steps for synthesize a compound, so A, B, C, D, and E, right? So with that, so they would take a little bit of the B, C, and D as well as the E, right? So with that, and they would put this in a bank. They would bank these, stuff like that, and then they would do high throughput screening on these things, stuff like that, and so they would see what stuck, stuff like that. So and from there you can get sort of like beginnings of saying like, oh, well, that this well on plate 4, sort of well, I don't know, D8. Right, gave a compound, and so you go and you would go and look at it and say, oh, that's the structure. I know what the structure of that compound is. That seems to work pretty well, and stuff like that. And so then you can start building off of that compound. It worked, it worked. I mean, stuff like that. I don't know if it worked well. We're sort of getting back, there. This was realized that there's a lot of effort being put into this, a lot of wasted sort of stuff, and so they've sort of dialed back from that because there's a lot of really good crystallographic information now, and so like that. And so what they're doing now is it's called high content screening, and so what they're doing is you can run these they're called libraries. These 100,000 compounds. What you can do is you can do it in a computer first, and see if any of those, and if it takes, a week to run through the computer, that's fine. You save all of the plates and robots and that kind of stuff, with that. And so you can run this through a computer first and see what sticks, so with that. Or you can, that you can sort of see if there's like groups, like this group seems to stick pretty well in this part of the binding site, and this part sticks pretty well in that. So how do we design a molecule? There's a lot more computational work now. So with that, and they're trying to, instead of screening 100,000 colonies or 100,000 wells, let's screen 100 and try to get some really good information off of that 100. And so with that, sort of high content screening instead of high throughput screening. So with that, but this is an important stuff, and they still do this. So with that, so it's something to be aware of. So with that, so okay, good luck.